Greetings once again and welcome to my new calculus channel. My name is John Gabriel, and today I'm going to be giving you a little challenge in a Pithy video on topics that I've talked about before, but that you may have missed out on some of the concepts, or that you may still have some questions about. So without further ado, let's begin. Now, if you recall, okay, this is going to be the last part of my presentation, so let's go over here. If you recall, some time ago, I explained in great detail what is a number, okay? And basically the number is the measure of a ratio of magnitudes. So I want to quickly realize a few of these concepts of ratios without the use of numbers. So let me show you how you can realize them. So remember I told you that you could denote ratios by placing the antecedent on one line of a similar triangle and the consequent on the other line, so that you have this particular ratio, then this ratio. Now in this particular case, you'll see that all these ratios are proportional. That means that if you take the measure of any of them, the measure will be the same, but they're proportional. Does that make sense? Okay. So we can understand cancellation by simply reducing the sides by the appropriate measure, or the appropriate line segment, as you see, which are these magenta lines. And now in geometry, there is no such thing as an irreducible fraction. You can just keep going all the time, you know, innumerably many parallel lines, and as long as you don't touch this particular vertex here, you'll always have a proportional fraction. Does that make sense? And what I've done here on this side of the page, this ratio here and this ratio, I'm representing this line to this line using this ratio, and this line to this line using this ratio. And my comment is that we cannot add these above ratios unless they have the same consequent, okay? Which would mean that we'd have to express both of them with the same antecedent. And in this case, if we did that, they'd be equal because they are proportional ratios. But supposing we have another ratio, as you see in blue here, and we want to give these a common magnitude. So how would we do that, right? Well, so we'd have to basically move this so that it's positioned over there. And now this red ratio with this red line and this red line is represented by this consequent, okay? This antecedent and this consequent. And of course, the blue ratio is represented by this antecedent, which I should have made blue, I suppose. But anyway, okay, it's never too late, I suppose. Here goes color blue. Okay, so now they have the same consequent, and we can just add the two if we want to find the sum, or we can subtract the shorter line from the longer line to find the difference. And of course, if you put in labels, you'll see that all of this makes sense, because this ratio here is 1/2, okay, and the blue ratio is 3.5 to 7. And I did it the other way around. I should have actually made this one blue and that one green. Never mind. it is quite late in the day for me. So let's show the axis, and there you can see the axis now as well, right? So remember now that in geometry we do not have numbers. So everything is done through ratios of magnitudes. And this is what I'm going to ask you today after I explain something to you. So over here we have these two line segments. This one here is pi, the constant pi. This is the constant square root 2, and this is their product. Okay, and of course, as you can see, we can take find the quotient of this blue line by the magenta line. It will be pi, and if we divide by pi, it will be this line here. And what this is telling you here in the geometry is that both these numbers, not these numbers, these constants, these constant magnitudes, so I can just hide the labels, both the red line and the green line divide exactly into this blue line. Now, think about that very carefully. You cannot do this thing in algebra. It's only possible in geometry. And moreover, it is only possible in this scenario. So for example, if you have to take any other pair of similar triangles, so let's say we took this small similar triangle to this one, then it's no longer true that this short magenta line times this red line, or the product of the two, will be the blue line. It only works if the similar triangles have at least two vertices on the circumference of a circle and they meet in a common vertex. So that's the only time that this theorem will hold. And the challenge to you today is to explain why this is the case. Okay, and you can write in the comment section why you think it's only true in the case of a circle and nothing else. And then of course in the next video we'll talk about maybe how you came across the answers. All right, so I would like to recommend two new articles, especially if you're a math teacher or even if you're a student, but this is a very short article for high school students, and it basically tells them how to get number from nothing without all the deep, profound details. And then of course another one on what is wrong with many of the mainstream calculus publications, such as the ones from James Stewart. For example, James Stewart will tell you that there's something wrong with this equation here, this one that I'm pointing to here, and that's absolute rubbish. This is a very valid equation. There is nothing wrong with it. And of course, I explain to you all the details in this article, and I'll place links to both articles in the details section. So if you haven't already become a subscriber to my channel, and also contribute at my GoFundMe link. Remember, I am the most persecuted mathematician in history, by the way. So no one else will care. And in fact, they do not want me to be publishing these facts and this knowledge. They want you to remain ignorant. They want you to remain in the dark. And I am fighting against that, not only for you, but also for your children. So my name is John Gabriel.